Hello and welcome. In this video, we're going to take a further look at matrices in general. Rather than just talking about augmented matrices as a way to represent a system of equations, we're going to just take a look at a matrix in general, which is just an array of numbers arranged in rows and columns. Now, when we talk about the size of a matrix, we refer to its size as m by n, where m would be the number of rows first, and n would be the number of columns. It is important. An m by n matrix, like a 3 by 4 matrix, is rectangular, but a 4 by 3 matrix is rectangular with the opposite dimensions, so the order is quite important. Now, we can also have a little notation that represents the entries in a matrix. We usually use a lowercase letter to represent an entry in a particular matrix, and in the I row and j column, we would just have two subscripts, Aij. Again, making sure we have row first, column second. Now, if we have two matrices, we can compare them. The only way that two matrices are equal is if they have exactly the same size. 3 by 4 must equal another 3 by 4 matrix. And if their corresponding entries are equal. So A11 must be equal to B11 of the other matrix, and A12 needs to be equal to B12 of the other matrix. Again, we use lowercase letters typically for entries, and we tend to use uppercase letters to represent matrices. Now, once we've got an idea of just a matrix in general, then we can start performing operations on multiple matrices by adding and subtracting them or multiplying them. So let's take a look at the easiest operation first, addition or subtraction. With addition and subtraction, it's a fairly easy operation on matrices. First of all, we can only add or subtract matrices that have the exact same dimensions. And then we can simply add or subtract the corresponding entries in the two matrices to produce the entries in the new matrix. So, for example, if I want to add these two matrices together, that would be allowed because they are both 2 by 3 matrices. And then adding corresponding entries, we can end up with the first entry in the first position, first column, first row. 3 plus 0 is 3. In the first row, second column, 5 plus 1 equals 6. And we can continue this for the remaining entries. Now that is pretty straightforward on its own, but remember that the two matrices have to have the same dimensions. If I wish to add 2, 4, negative 1, 5, and a matrix negative 1, 3, 4, 2, minus 5, and 3, this would be undefined. Another basic operation is called the transpose of a matrix. The transpose of a matrix is simply taking an m by n matrix A with elements Aij and flipping it diagonally so that we end up with an n by m matrix where the rows and columns are swapped and the new elements are Aj. So a quick example of transpose. If we let A equal 3, 5, negative 2, 1, the transpose we would write as A with a little superscript t. And it's a diagonal transposition, so the 3 will stay where it is, and the 1 will stay where it is, but the 5 and the negative 2 will swap positions. And you can see that the first row, 3, 5, is now the first column, 3, 5. The second row, negative 2, 1, is now the second column, negative 2, 1. But if we have a rectangular matrix, and let's say we have an example B, which is 3 by 2, then our transpose is now going to end up being a 2 by 3. So why don't we look at the first row of B and make sure that we can now put that in as the first column of B transpose. Second row becomes second column, third row becomes third column. And that is the transpose operation. Another very basic operation is scalar multiplication. With scalar multiplication, we can take any matrix A and multiply it by just a real value. We'll call that value C, also known as a scalar. Now, when we write C times A, we are going to multiply each element of A by C. So that won't change the size. We'll end up with exactly the same dimensions, but each value will be multiplied individually by that value of C. All right, here we have a matrix A, and if we wish to multiply that by a scalar, then we can just say something like 2A and multiply each element by 2. We can also write 0A, but that will just make each element of the matrix equal to 0. And this is where we might end up with a little bit of a confusing notation happening. A zero matrix we often just denote by 0 when we're talking about an equation involving matrices. So this particular matrix here, we might just call it 0. That actually refers to the entire matrix, not just the number 0. It's much easier when we're actually typing mathematics out on a sort of proper document. We would probably make this an extra bold 0, and that would end up meaning a matrix, whereas a single entry in this matrix would just be 0 and not be bold. Pretty hard to make bold letters, unfortunately, when we're just writing mathematics out on paper. But you may see this in various different forms. When we're adding 0 to a matrix, it makes sense that we would treat that 0 as a matrix. So writing, in fact, A plus 0, we would say is well defined as just equaling A. But what we really mean there is we're taking our matrix, -5, 2, 0, 4, -3, -1, 1, 6, and we are adding a 0 matrix of the same size, so that addition is defined, and we end up equaling the original matrix A. Whereas when we write 0 times A, we can understand that that is probably just the 0 being a scalar multiple. If it's not clear in a question, then it's worthwhile to ask, but most of the time the meaning is fairly evident from the context. Now, what about multiplying two matrices together? Well, I'm going to save that for a future video because that's actually a much more complicated operation. So keep this nice and short. Those are some very basic properties of matrices and some basic operations. But we'll take a look at matrices that are multiplied together and see how we can tackle that. It's not quite as simple as multiplying two scalars together. Unfortunately, it's a much more complicated operation. So I'll see you in that video, and thanks for watching.